Okay, so um, in the previous classes we worked on the PD controller. We developed the code in MATLAB and in Simulink, and in MATLAB coding we had also ODE solver, and we embedded PD controller in the MATLAB code that I shared with you. For this system, that was y over u, theta over u pendulum was 1 over s square plus omega n square. So we added the PD controller to this. By doing that, we had the desired theta. Because we are continuing today, I teach you PID controller. To this, I'm going to talk about I controller. So, and plus minus. So we had this Kp proportional plus Kd in S. Then this goes to the open loop transfer function. Here we go. By giving you signal, control signal U that we plotted in ODE and also in the Simulink of 1 over S square plus omega n square. This gives you theta. This is being compared with the desired input that we set that in the code of the MATLAB to 60 degree, 30 degree, whatever you want, right? And this was the tracking error. So what we did, simple in control, and after graduation you have to do, you need to design this U. Right? So for PD part, we said that the U is simply Kp plus KdS in E, right? In E, see UE, transfer function. And we tuned Kp and Kd, right, to change this marginal stable system to a system with the given parameters that your boss wants. That the maximum overshoot, if I remember correctly, because I'm teaching from my mind, was 25%, and peak time, if I remember correctly, was 0.2 seconds, right? Peak time. So based on this, we designed Kp and Kd in the previous classes, and we simulated in MATLAB, right? Well, so now, as I told you, now the open loop transfer function of your controlled system is this, your new G, your new G. So your new G in your notes that you have in the previous class is Kp plus KdS, just multiplying two blocks, in S square plus omega n square. And you know that the closed loop transfer function of this, as you have in your notes, is Kp plus KdS in S square. Now you are adding the missing S from here. Kps plus Kp, this is D, Kd, S plus Kp omega n square from the previous class. So why I'm writing this, because when we plotted in MATLAB ODE this controlled system, we saw that the angle was doing this. Suppose that you want to keep it at 30 degree. I'm gonna develop the MATLAB code today more by adding the I controller. So this is 30 degree. You saw that it was doing this, see? Right? By giving that 0.2 seconds as the peak time, as your boss wants that you design, and the maximum overshoot of 25%. But we have a small value of the error signal if you observe that. E, steady state. So we have to fix it. We have to remove it as control engineer that you are graduating from mechanical engineering course. Okay. But before going to I, which does it for us, removing the steady state error signal, I controller or integrator, okay? Let me take you back to the middle of this semester and calculate steady state error signal, final value theorem, that was S theta of D input to the system. That's right. And 1 plus G, but your G is new G because you added controller. This is your new G, okay, because you added controller to the system. When S goes to 0, right? Okay, everyone. So your input to the system, for God's sake, say it is 60 degree, but this is a unit step. That's right, this is a 30 unit step. So 13 unit step. I plotted here. This is radian. So it's gonna be the limit of S. What's the Laplace of this, guys? This backs to the first day of this class. Laplace of this, yes, pi over 3 over S, because this unit step is over S. Gonna be pi over 3S. 1 plus your new open loop transfer function, Kp plus KdS in S square. You saw that I got a very physical problem of the pendulum. I'm step by step controlling as I want, because this example continues, this class and the next class. When S goes to 0, so you see this S goes to New York, and this becomes a limit of pi over 3 S square plus omega n square plus Kp plus KdS, and this goes up, bingo here, S square plus omega n square. When S goes to 0, this S goes to 0, this S goes to 0, this S goes to 0. So steady state error signal of this system gonna be this, Kp plus omega n square. So you see it's gonna be very small value. Why? Because omega n square of this system, I mean this, was 9.81. Remember? Natural frequency of the system, G over L. We said the L is 1 in the code. Remember, everybody? Length of the pendulum is 1. So omega n gonna be G over L. So L is 1, omega. So if you are done, I will go to the next page. Are you done? Okay, it's recording, for God's sake, but it's very important, yeah. So let's continue. ESS, steady state error signal, was pi over 3 omega n square in the Kp designed pendulum omega n square. So we said the omega n square for the pendulum natural frequency was 9.81. Can you look at your notes and let me know what's the proportional gain that we designed? The number to me. I can open the MATLAB code, but I want, if you have it, to let me know. Not KD, KP. Yeah, can you please, if you have in notes. Actually, 208. Let me do it. 284.97. That's enough. So you're gonna see a steady state error signal of this is 9.81 multiplied by pi over 3, so 284.97 plus 9.81. So let me use my calculator because, as I told you, I have no notes. I'm teaching from my mind. And calculate the steady state error signal. It's going to be very low value, obviously. So pi divided by 3 multiplied by 9.81, and this divided by 284.97 plus 9.81. Bingo. So as you saw in the MATLAB code, it was a small value, 3.5. Remember? If you remember, it was a very small value. But this is still a number. See what I'm saying? It still is a number. So you have a steady state value. So I want to remove it. Okay, good. So here you get to know I controller, integrator, I controller. Saying that, I'm gonna take you back here and delete all of this. So I'm going to take you back here. So this time I controller, so U over E, if you have only I controller, is, oh, let me do this one time. U over E in time domain gonna be integration of error signal. Is this, as its name says, I controller. So if you have the Laplace transform, go to the frequency domain, U over E gonna be, you know that the integration, Laplace integration is 1 over S. So you're gonna have, oh, sorry guys, I'm stupid. So it's gonna be what? E over S. Or simply U over E is 1 over S. But we add again Ki for that to tune it. Ki over S. So when I say PID controller, we added proportional derivative to stabilize system and tune transient response. Now I'm adding I controller Ki over S. I controller to remove steady state error signal. Steady state. So I controller fix steady state part of the response. Steady state part of the response. PD controller tunes transient response. So this is function of PD. This is function of I to modify the system. Everybody clear? Now, so when I say PID, this is complete set. Here we go. PID controller that you can find this in 99% of the all industrial systems. Name it from airplane to satellite to the Mars rover to whatever you want. Okay, you can find PID. Any moving dynamics that is being controlled. Even your home cooling and heating system. It can be a PD system. Okay, controlling system. So why PID is very effective? The question, before going ahead in mathematics, why it is very effective? This backs to high school, guys, not to university level. You have a given function like this, whatever, f. When I say derivative of this function, what do I mean physically? What derivative at this point, guys? Exactly. So this is slope. It means that luck has that you put an I here, and you want to see how it's gonna change. That's right. Yes, derivative, or how it's gonna change from here, or how it's gonna change from here. So it's looking the how it's gonna change. Looking at where? At future. So when I say derivative, simply and physically and fundamentally, in lay language means future. When I say integration in high school, what does it mean? Integration of FDT. What does it mean in the graph? Yes, yes, area under the curve. You mean that if you want to have the integration from 0 to T naught, mean everything before this point. What does it mean in lay language, simple language? You tell me. Before. This is future. This means past. Right? And when I say derivative term, just Kp multiplied by error signal means present. Right now, multiply error signal with a number, just present. This means now. So PID is very effective because predicting the future of error signal, seeing the past of the error signal, and tuning the present status of the error signal. See what I'm saying? Yes, everybody? Yes? Everybody understand what I'm talking about? So PID means this. Now, let's continue. Going to the MATLAB coding, now I added the PID controller to the pendulum that was marginally stable originally. So theta of d, we added PID. Here we go. Ki over S plus Kp proportional plus KdS goes to omega 1 over S square plus omega n square. This is U, this is theta, this is being goes out. Here we go. So now your new open loop transfer function is this G new. So your G new gonna be, if you multiplied everything here, guys, you're gonna have Ki plus Kps plus Kds square divided by S multiplied by this numerator. That's right. And this is gonna be S square plus omega n square. This is your new open loop transfer function. So this is equal to Kds square Kds square plus Kps plus Ki divided by S cube plus S omega n square. Now, after adding PID controller, now let me examine steady state error signal. Limit of S theta d 1 plus nu g. So again, this is whatever. Say you want to keep theta d at a angle unit step. So you're going to have a 1 over s 1 plus kds square plus kps plus ki divided by s omega n square plus s cubed. This with this goes to New York. So you have a limit of, this goes up, s omega n square plus s cubed divided by whatever, because you have a constant number here. Whatever, s goes to 0. 0, 0, 0. See what I'm doing? Yes? So we change the steady state error signal to 0 mathematically by adding I controller, by adding this word. Everybody understand? Yes? Great. So, by saying that, I'm going to MATLAB, because now you have to know how to develop its MATLAB code, for God's sake. Actually, we have it, we just have to develop it. So it's going to be MATLAB. Okay. Okay, there we go. We'll work with this. So, this is our PD controller, right? So here I'm gonna say Ki is 50, just to give a number. So here you're gonna have this is your PD controller, right? So you're gonna have Ki in what? In your I controller. Okay, guys, I taught you. If you look at here, in time domain, what is that? Is integration of EDT. Integration means sum under the area, or sigma. That's right. Sum of this area under the curve. So what you can do is this. You can say, okay guys, you know that this means you put error signal in a vector. That's right. Remember from the previous class? Yes? So what I'm gonna do, I'm gonna say I part is, there's a command in MATLAB sum, exactly, that summing all elements of the vector until that point. So I'm gonna sum of EP. Okay, sum of EP. Let me pause for that. I want to show you how it does. Okay, so here we go, guys. See, look at this. See, I increasing. That's right. IP. That's right. Do you see that? Yes, everybody. Do you see it?
Yes.
Here we go. So it's summing all the E as a vector. That's right. But as I taught you here, is integration E in dt, step time. So because in average I said dt is, here is, let me do that for you. I say time step, I'll define here, is 0.01. We can say here 0.01. Oh, sorry, t step. Sorry, I'm gonna define it here to make it coolable. T step. This is a very fundamental way of teaching control. Okay. And T step. So this means integration of EP in time step. Okay. Now you have this integration of EDT, but as you know, it has a KI multiplied by that. So I'm going to define, and I'm going to say KI multiplied by integrator. Everybody understand now? Yes? This is gain of P controller. This is gain of D controller, because I'm going to share it with you. This is gain of I controller. So this is int integration of E dt. Right? But integration in MATLAB coding means sum that vector in what? In T step. Okay. Even that you put T step here, you can put inside here. It doesn't matter because it's a constant number. Okay, it's a constant number. So clear, guys? Yes? Now let me run it. Let me run it. Okay, this is the control torque. Tau. Error signal before going to some number now goes to where? You tell me. Goes to where? Error signal goes to 0. We made it 0. And now this is what? Velocity goes to 0, obviously, angular velocity. And bingo, we're gonna keep it as 45 degree. Look at here. Where is that? Which angle we want to keep it? Where's theta d? Oh yeah, 45 degree. Okay, and it goes to 45 degree. Where's the graph? Goes exactly to 45 degree. Here we go. Everyone understand? Yes. Now let me change play. You see that the margin stable system you made is stable. So let me change this and put 10. The pi integrator. Let's see what's the difference between them. Tau 0. See? Happened much sooner. Error signal. This. And this is very close to what you wanted to design, guys. That we wanted to have the peak time in 0.7 and 25% of error signal. So you have to play with the KI, see what I'm saying? To give you that 25% error signal. See what I'm saying? Yes, everybody? So don't give it, because you have to satisfy the original. What was the original? Original was, what was that? Control PD. Yeah, original was 25% overshoot and 0.2 seconds of what? Peak time. See what I'm saying? See here? So now if I zoom this in, 0.2 peak time and 25% of overshoot. Almost. See what I'm saying? But if you increase KP from 10 to what is that? From 10 to 50, where are you? Oh, here we go. 10 to 50, this is not what you wanted to have as a control engineer. You get error signal to 0, but much slower, and see what happens for peak time is the same, but this may be different. See what I'm saying? Okay. So, and I don't like this slow convergence to 45, because in the previous case it was not like that. In the previous case of 10, it's a trade-off game. This is you that you have to select. See, this is better profile and more logical to me, at least. See, ping at 1 second, settles in at 1 second. In previous game it was settling down at 4 seconds or 3 seconds. I prefer this. See what I'm saying? You are the control engineer. You have to select a specification that you wanted, error signal to 0 and whatever. See what I'm saying? Are you following me? Yes? Good. Okay, before continuing, okay, let me go back to, before continuing, guys, don't forget, this is your G, right? If I calculate the closed transfer function, theta over theta d, you're gonna have new G 1 plus G, remember? This is now you have to know it. So your new G was KPS, as we did previously, KDS square plus KI divided by S divided by S square plus omega n square, meaning that you can remove this and put it here. 1 plus the same, KPS plus KDS square plus KI divided by S in S square plus omega n square. If you simplify these guys, you're gonna get this KDS square plus KDS plus KI, and you're gonna have S cube plus KDS square plus KP plus omega n square S plus KI. Oh, it's interesting. After adding I controller, look at here, guys. Don't write. By PD controller, we had second square system still. KD, KP omega n square. But after adding I controller, the system order increased to how much? 3. These are the same, but we added a KI here. See what I'm saying? Yes? Everybody? So if you want to have a good design, you have to go to the Rolf stability criteria. S square, S1, S0. This. 1 KP plus omega n square, kd ki, this is ki. It's gonna be kd multiplied by kp plus omega n square minus ki divided by kd. When the system is stable based on whatever I taught you, when the first column is positive and exists, means kd must be greater than 0, ki must be greater than 0, and this must be greater than 0. This is already positive. So kd in kp plus omega n square must be greater than ki if you still want to have a stable controlled system. So you cannot terminate this. If you terminate this, even that you give some gains, your system gonna be unstable. See what I'm saying, everybody? Yes? Good. Now, if you are done, I will move to the next problem of the PID controller. Okay. Now look at this, guys. Suppose you have this system. This is a open loop transfer function of a plant. Can be anything. Can be robot. For example, I'm saying. Can be the automatic door of a building. Whatever. Okay. Originally, this system closed loop transfer function gonna be 1 over s square plus 1 plus 1. Oh, plus s plus 1. This system has two poles. Let us find the poles of this system. Minus 1 plus minus 1 minus 4 divided by 2. Or this system gonna has minus 0.5 plus minus I root to the square of 3 divided by 2. This system is under damped, over damped, or critically damped system, guys. You tell me. Now you have to know it. A pair of complex conjugate poles. Yes? Which of them is under damped, critically damped, or over damped system? It's under damped system. So it means that if you apply a step as input, here we go. X, T, step as input. This system gonna behave like this. Right? But sometimes for robotic systems, or you have seen that we have some doors that you don't wanna, after opening, they're gonna be closed automatically, but they never oscillate when they are closed. See what I'm saying? They're gonna do like a critically damped system. It's gonna be damaging. Some system under damped system is not good. You wanna change it to the critically damped system. You don't like the oscillation on those systems. Even in robotic systems, we don't want to have oscillation, even transient. See what I'm saying? Because if this is a robot, and I want to go from here to here, okay, here, I don't want that this goes and does this and stops. Why? Because maybe here and here there is an obstacle that's going to damage that. See what I'm saying? Yes, everybody? So this underdamped behavior is not favored in all applications. So you have to, as a control engineer, you have to change it to the critically damped system without oscillation. Understand? Everybody? Good. Now I'm telling you guys, you know what? Imaginary, real. Here's 1, 2, 1, 2, 1, 2. This system original poles are here. Say original poles, these poles. I'm telling you, you know what, guys? You are my control engineer, I'm hiring you. Go and find a critical, this is under damn system. Design a controller for me that its desirable poles, your new poles, are at -2 here. And critically damped system means they are 2 repeated poles, remember? That's right, real poles. So it means that this is, remember, if you go to notes, it's minus zeta omega n. Remember, everybody? Yes? For critically damped system. So guys, can you remember or go to notes and see what happens for zeta when the system is critically damped? What happens for zeta? Yes. So it means your zeta is 1 already. See, now you see the translation of the terminology that we define in this course. By saying that, if your boss says that have the desirable poles at here, you can calculate omega n is how much? Omega n is how much? 2. Everybody understand what I have done? Yes? Good. So now, okay, let's do that together. I'm gonna add the PD controller here. To change under damped system to what? To critically damped system. Let's do that. Like as the previous case, not case. Okay, plus minus. You have a PD controller, KP plus KDS. Why PD controller? Because PD controller changes transient behavior. Are you following me? So, and this is the open loop transfer function of the system originally. S plus 1 y x, here we go. Now your function is to tune KP and KD. Great. So you know that y over x closed loop transfer function after adding the controller, all transfer function gonna be again KP plus KDS divided by S square plus KD plus 1 in S, right? Sorry guys, because I'm doing with you, I have to redo it. So your new Gn gonna be Kp plus Kds in S square plus S. So closed loop transfer function gonna be Kp plus Kds in, this is Gn 1 plus Gn in S square plus Kd plus 1 in S plus Kp. Everybody clear? Yes? Okay. So guys, this reminds you what again? This reminds you what? S square plus 2 zeta omega and S plus omega n square. Yes or no? So, but we already, based on the request of your boss, we calculated omega n. Because your boss said make it here to the damp, remove the oscillation, we know that zeta is 1. So, this is 2 multiplied by 2 is 4. This is 4. Clear, everybody? Yes? So, KD plus 1 gonna be 4 and KP gonna be 4. So KP gonna be 3. So you design that. Clear, everybody? Okay. That's it. So, on the other hand, your Y over your control system is KP. Let me see. KP is 4. This is KD, guys. Okay, KD. It's gonna be 4 plus 3s s squared plus 4s plus 4. So if I didn't mistake any numerical issue, let me model it in MATLAB, if you let me. So I'm gonna see clear all, close all. I'm gonna say num is equal to, I set KP equals to how much? 4, and the KD equals to 3. Num for the closed transfer function is KP plus KDS 0 KDS in KB, and then was 1 KD plus 1. I'm just doing parametric. Here we go. Plus KP plus KP. So if I say figure 1 and step num and then and greet for me, and I say critically PD controller in ME530. Okay. Let me double check the numbers because I draw it with you. So 2 was 4 KP4 and 2 by 2 4, so KD plus 1 was 4, KD is 3. So KD is 3, KP is 4. Okay, and if I run this, it must gives you a critically damped system, unless we did some numerical mistake. Almost gave us, almost. See what I'm saying? Almost gave us a critically damped system. Now let me compare this, bear with me, with uncontrolled system. Then 1, 1, 1, 1. Remember this? Hold on, guys. Remember this? See? 1, 1, 1. Uncontrolled system. So if I say, hold on, step num1 and then 1. This is red, this is blue. Now if you can see the difference. Here we go. This is under damped system. Almost we change it to critical damped system. See what I'm saying? Yes. Now you're gonna say, okay, remote payment. Why it still we have still? I'm gonna say, you know what? For doing that, let me change this to 5. Huh? If I change it to 5, omega n is gonna be 5. From here, I move it to here. Okay? When I do that, omega n gonna be 25. So Kp gonna be 25. Let us do that. Kp gonna be 25. And your Kd gonna be, what is that? 2 in 5, 10. 10 minus 1, gonna be 9. Everyone agree? Gonna be 9. I'm gonna change it to 9. Let us see how it behaves. Oh, it is being worse. Not under dam, but you have more overshoot here. See what I'm saying? So you have to play with desirable pole to see what exactly gives you a critical dam system. Okay? So, and that's it. But let us stick to previous version. Here we go. Okay? 4 and 3. Yeah. So, and I say time 0.04. Oop. 0.010 and time what? SS? What is SS? Where we used SS? Do we still use SS? Oh, so I think you have to put how I was doing that. I forgot that. My mind is getting older, guys. No, it's not like that. But I forgot that for now. Okay, I don't want to give you a wrong answer. So you see that we changed the under-damped system to almost critical damped system. We will remove these oscillations. See here? It never goes down back and goes up. Or let me try by saying instead of the zeta 2, I'm saying to 1. I'm gonna make it to 1. So it's gonna be 1. Omega is gonna be 1. Here it's gonna be again 1 Kp. It's gonna be 2, so it's gonna be 1. So let's just see that. Kp gonna be 1, and this gonna be 1. Now let me see this. Here we go. We did it. So you can say to your boss that having the poles, your desirable poles, critical damped system is 2 works, but it gives you a little overshoot. So let me change it to pole desirable at 1 instead of 2, and then do the calculations for the KP and KD. Put in the code, original system, critically damped system, no oscillation. Everybody understand what I have done? Yes? So for the robotic system, that sucks. It's gonna damage the workspace. You have to avoid the oscillation. So you as control engineer, you have to play with the desirable poles and the behavior that you want to have. Okay. So as a homework for yourself, I'm your boss. Suppose that I hired you. Go and design a PD controller for me that has 2 poles at -2 at -4. What does it mean based on the terminology I taught you? Under damped, critically damped, or over-damped system. When you have 2 real distinct poles in the left-hand side, what's the name of that? Over-damped system. I'm asking you when to design an over-damped system here. Design a PD controller for me. Okay? Everybody? So next class I'm gonna finish the PID controller and give you some very introduction to root locus, and we are almost done with the class. Okay? Thank you.